Hi, my name is Gustavo Melendez, and I will be presenting our research work titled Topological Properties of Rare Earth Hydrides, a first principles study. So starting with introduction, the research on compounds containing or doped with rare earth elements has gained significant importance over the last decade as their electronic configuration allows the or f orbitals to distribute in energy sublevels, creating available energy levels for their outermost s or p orbitals, which can benefit bond formation. Additionally, compounds formed with rare earth elements can exhibit metal transition properties. Moreover, interesting compounds formed with rare earth elements and hydrogen have been observed. Some examples of these compounds being investigated include lanthanum decahydrogen or cesium decahydrogen, as they exhibit metallic properties at high temperatures and pressures. In our work, we investigate the compound lutetium hydride in its pristine form and replacing one lutetium atom with, with one yttrium or lanthanum atom. We have also considered replacing the hydrogens by lithium. We present their electronic properties considering per orbit coupling. Methodology: to obtain the electronic properties of the hydrides formed with lutetium, yttrium, and lanthanum, we used the quantum espresso computational package. The methodology employed to obtain the crystal lattice constant, band structure, and density of state for these compounds was based on density functional theory, considering the generalized gradient approximation using the Perdue-Burke-Ezenhoff exchange correlation functional. The Pau method includes the Grime D3 scheme for van der Waals interaction. And finally, the use of pseudopotential. For our calculation, a convergence threshold for the total energy of 10 to the minus 6 electron volts and 10 to the minus 5 electron volts about angstrom for the force between atoms was considered, with plane wave kinetic energy cutoff of 70 Rydberg and integration of the first Brillouin zone with a much compact mesh of 20 by 20 by 20 centered on the high symmetry gamma point. All our calculations include spin orbit interaction. The next section, results. Our results show that lutetium hydride has crystalline lattice constant A equal B equal C equal 3.53 angstrom, with angles alpha equal beta equal gamma equal 16 degrees, indicate that these compounds belong to the space group FM3M, as shown in figure 1. These results are consistent with those reported in literature. The band structure and density of state for these compounds are shown in figure 3. The electronic band structure for lutetium hydride is shown in figure 3a. We observe a metallic behavior as the separation between the valence band maximum and the conduction band minimum is zero. In the density of the state, we notice that the lutetium atoms, the orbital has a greater contribution, including spin-orbit coupling, results in a separation in the band structure suggesting a splitting of the degenerate levels, which can have implications on the application in spintronic basic device. Replacing the lutetium atom with lanthanum show figure 3D or yttrium figure 3G, we observed that these new compounds maintaining the band splitting, and that the orbitals of these atoms have the greater contribution. The density of states of all three are very similar. Most of density is a conduction band. Lanthanum show a swift high energy and, and there is a peak near the Fermi level. In the band structure, we observed that the conduction band at W was minimum is the Fermi level, shift is higher energy for lanthanum and yttrium. We also show the results of replacing one by one the hydrogen with lithium. These results suggest that the inclusion of the lithium atom in these hydrides invented the metallic behavior observed. For all three compounds, the density of state shifts lowers energy with an increasing of states in the balance and reduction in the conduction band. The band edges are swept downwards and the metallic behavior is mainly due to half-filled bands and thus a different metallic behavior. Finally, post-calculation charts analysis results suggest that hydrogen and lithium atoms in these compounds work with a balance of -1, as shown in figure 2. Conclusions. In these compounds, the effect of spin-orbit couplings played an important role as it separates degenerate energy levels. Including lithium atoms in these hydrides retains the metallic character, with the greater contribution to the density of state coming from the d orbitals of the d rare elements. Lithium compounds do not show a topological behavior. Thank you very much for your attention. I would like to thank the collaboration of this work. Dr. Luis Enrique Sansores y Cuevas, doctora Roxana Mitzayer del Castillo Vázquez, doctor Raúl Arturo Espejel Morales y doctor Alipio Gustavo Calles Martínez.